Hello, hello. Am I audible, guys? Today's contest was tough. Yeah, it was tough. And also, I think the checker was wrong. Like for div 1A or div 2B, the checker was wrong. Like initially it showed wrong answer, but after some time it showed correct answer. So that like messed up the contest. Anyways, let's start. So hi everyone. Welcome to the PCD of today's CodeChef Starters 178. And today we'll discuss the problems A to E of div 2. All right. But before we start, I would like to tell you about our CP31 sheet. If, in case you didn't know, this sheet contains 31 handpicked problems from each rating from 800 up to 1900. Our sheet has been upgraded with a live leaderboard and also an interface which syncs your CF account with the sheet, and it automatically like tells you which problems you have solved, right? And also it contains a discuss section where you can do comments on the problems and discuss with your peers. And also every week 7 to 8 solutions, video solutions, will be released on our YouTube channel, so you don't have to search for that. The link to the sheet is down below. So let's get started with the PCD now. All right, so we'll discuss the first 5 problems of today's code chef, that is in div 2. All right. Okay, so the first problem was placing 0 1 and 1 0. You have x 0 1 strings and y 1 0 strings. You will form a new string s by first rearranging these strings in some order and then concatenate them in this rearranged order. Let fs denote the number of indices such that s of I is not equal to s of I plus 1. Find the minimum possible value of fs. Okay, so the problem says that we have strings. We have some x strings which are 0 1 and y strings which are 1 0. Okay, and we have to rearrange these strings in any way and then concatenate them. So for example, if x equal to 2 and y equal to 1, then we have two 0 1 strings and a 1 0 string, and we can rearrange these strings however we want. And our goal is to minimize f of s. So s is the final string that we make. So like if we rearrange these three strings, let's say we rearrange it like 0 1, 1 0 and 0 1, and we then concatenate them. So we do concatenation, so it becomes 0 1 1 0 0 1. All right, so this is s, and our task is to minimize f of s for all possible rearrangements, right? And what is f of s defined as? F of s is defined as the number of indices I such that s of I is not equal to s of I plus 1. So we need to minimize the number of indices such that s of I is not equal to s of I plus 1, right? So it is binary string, right? So binary string means that either s of I is 0, I plus 1 is 1, or s of I is 1, s of I plus 1 is 0. So in both of these cases, they will be counted in the f of s, and we have to calculate the minimum value. We have to minimize this f of s, right? So one way to think about this. Okay, before that, let's look at test cases. Like one test case, if we look at this 1 comma 2, 1 comma 2 means that we have a 0 1 and we have two 1 zeros, 0 1 1 0 1 0. So if we like rearrange it like something 1 0 0 1 1 0, then it is optimal. Like I'll show you why in the recent future, but right now let's look at what is the fs. So for this string, like I concatenated this, and for this string, the value of fs is like 1 2 and 3. Like these three indices, this index, and this index don't have the same number after that index, right? So therefore, f of s is 3. And for this combination, like 1 and 2, this is the minimum value of fs. I will prove that. So that's why the answer is 3, right? So now, how to solve this? Like, how can we think about this? So one thing to observe is that, okay, first of all, f is defined as the number of indices where s of I is not equal to s of I plus 1, right? So can I write this as total? Like, can I write f of s as the total number of indices minus the equal ones, s of I equal to s of I plus 1, right? Like in this case, string s has length 6. So total there are 5 indices for which you have to check I and I plus 1. There are 5 I comma I plus 1 pairs, right? So total is 5 in that case. And if we subtract the equal strings, I mean the equal indices. So this index is equal, I mean these two, and this index is equal. So 5 minus 2, which is equal to 3, right? So that's what I can write, that number of indices such that s of I is not equal to s of I plus 1. That is just total minus number of indices such that s of I is equal to s of I plus 1, right? And however we rearrange the strings, this total number of indices won't change, right? Because that is just length of the string minus 1. And what is length of string? Length of string is just 2 into x plus y. Like 2 into x plus y is the length of the string, right? Because we have x 1 zeros, sorry, x 0 ones and y 1 zeros. So each of these have two characters each. So total number of characters is 2 into x plus y. And minus 1 we will do for the number of indices that we have to check, right? This total value is that. And then minus s of I is equal to s of I plus 1. This is fs. Okay. And we have to minimize this value, right? This total value we have to minimize. So essentially, this thing is constant, right? This thing is fixed, irrespective of what rearrangement we choose. So basically, we have to maximize this thing. We have to maximize the number of indices such that s of I is equal to s of I plus 1. We have to maximize this. So basically, we have to maximize the total number of adjacent similarities. So like, okay, is that clear till here? Okay. So now if I see, like I have to basically rearrange x and y's. So I have some x 0 ones and y 1 zeros, right? So for a minute, I'll call this 0 1 as a, the string a, and 1 0 as the string b. So basically, I have x a's. So a I have x times, and I have y b's. So b I have y times, right? And I have to rearrange these. I have to rearrange these to maximize the number of indices such that the consecutive things are equal, consecutive letters are equal in the binary string. So, what can I observe? The first of all, let's look at this example that x equal to 2 and y is equal x equal to 1, y equal to 2. So, I have an a and I have two b's, or in other words, I have like a 0 1 and I have a 1 0 and I have a 1 0. If I use a yellow color, okay, 1 0. So now actually, if you can observe that inside these different strings. Like if I say that 0 not equal to 1, right? So however I rearrange this 0 comma 1 pair, so first of all it is going to be together, right? However I rearrange these letters, this 0 1 pair will be together in the final string. And also I can say that it is not going to contribute in the number of indices which are equal to each other. Like s of I equal to s of I plus 1 can never happen for this 0 1, right? And in 1 0 also it cannot happen. So the only way it can happen is when I join two strings of different kind. Like, okay, if I join 1010, they are of same kind, right? They are B. So if I do something like BB, then also it becomes 1010. So as we knew that these two wouldn't contribute, but also this one and this one are different. So they also don't contribute. So if we concatenate two string of different type, or sorry, same type, then we don't get any profit, right? But what we can do is concatenate two strings of different type. So let's say if I do a comma ab, right? If I do ab, then this part will give me one index. Like a is 0 1 and b is 1 0. So this 1 1 is an equal index, right? So that's the observation here, that this 1 1 can be counted in my s of I equal to s of I plus 1, right? So essentially, and also BA as well, that if I do BA, so BA means 1 0 and 0 1. So this 0 0 are the same. So essentially, what we can say that, let's say I rearrange some this like a comma a b b, like I have one a and two b's, and I rearrange them like a b b. So in this case, there is only one index. I mean, there is only one opposite pair. So the value of number of indices such that si equal to si plus 1, that will only be equal to 1. This is 1 because there is only one pair which is ab. Now let's say for example I have two a's and three b's. So if I do something like ba abb, then this ba, this ab, they are the only two strings which are opposite, the only two adjacent pairs which are opposite. So we the number of indices is that s of I equal to s of I plus 1, that is 2, right? But instead of this, if we do something like BA, we do alternate. Then 1, 2, 3, and 4. These four pairs we get. So the number of indices is 4. And as you remember, we have to maximize the number of indices which are equal, right? We need to minimize this total value. So we need to maximize this s of I equal to s of I plus 1. So how will we rearrange x comma y? We will basically alternate them, right? What we'll do is we'll basically do x y x y x y x y x, and maybe we'll run out of y at some point. So we'll do x x x x, right? So this will give us how many? This one, this one, this one, this one, this one, and so on. It is tough to understand AB compared to 1 0 1 1 0. Okay, so see, I have, let's say I have some 0 1. Like what I want to just say is that if you put, let's say you have three 0 1s and two 1 zeros, then what you can do is, like if you place the opposite kind together, like this is one kind and this is the opposite kind, 0 1 and 1 0 are opposites. So if you place them together, then you will get one pair. I mean, you will get one index for which s of I is equal to s of I plus 1. And if you place the same pairs together, that is, if you place 0 1 0 1, then you won't get any index for which um, the s of I is equal to s of I plus 1. So what you will try to do is you will try to put opposites together as much as possible. So basically what you can do is you can just put alternatingly. Like first you will put 0 1, then you will put 1 0, then you will put 0 1, then you will put 1 0, then you will put 0 1, etc. But at some point you might run out of either 0 1 or 1 0, right? So in that case you have no option but to continue just doing 0 1 0 1 0 1 0 1, etc. And they won't give you any index such that I equal to I plus 1, s of I is equal to s of I plus 1. But one thing is to, like, one thing to make sure is that, okay, let's say you have more 1 0 as compared to 0 1, like number of 1 0, that is y, it is greater than x, then you should start with 1 0, like 1 0 0 1 1 0 0 1 1 0 0 1 1 0, and then 1 0 1 0 1 0, etc. And the reason for this is basically, let's say I'll give an example. Okay, so let's say you have three 1 zeros, 1 0 1 0 1 0, and two 0 1s, so 0 1 0 1. So now if you had put like 0 1s first, so 0 1 0 1 1 0 0 1 1 0, so at this point you are out of 0 1s, right? So now you have to put 1 0. So here you are getting only 1 index, 2 index, and 3 index. But if you had started with 1 0, then you could basically interleave these 0 1s between those 1 zeros. So you do 1 0 0 1 1 0 0 1 1 0, and in this case you get 4, right? So 1 2 3 and 4, right? So in general, if you have x 1 zeros and y 0 1s, and let's assume that x is greater than or greater than y for now, because if it is less than y, then you can just swap them. Okay, so let's assume that x is greater than y. Then basically what you can do is put xy 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 xy, and then finally x, and then x x x x. So here basically you finish all the y's, this y, this y, this y, this y, right? And how many pairs have you gotten? You have gotten 1 2 3 4 5 6 7 8. So you put 4 y's and you got 8 pairs. Like if you have 4 y's and you have an x between all of them and before and after, then you will get 8 pairs. So in general, if you have y, then you will get 2y pairs, like whichever one is smaller. So I am assuming that x is greater than y here. So if x is greater than y, then you will get 2y pairs, assuming that there are sufficient number of x's. Like you can put 4 y's and 5 x's to get 8. But let's say you had only 4x and 4y. Then you have to put xy, 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 xy. And in this case, you get one less. Like you get this, 3, 4, 5, 6, and 7. So you get one less than that. So if x is equal to y, okay, like for x greater than y, we got 2y. And for x equal to y, we get 2y minus 1, one less. So this is the number of indices such that s of I equal to s of I plus 1. And finally, you will calculate the answer by putting that here, like 2 into x plus y minus 1 minus whatever you got. Okay. So yeah, that is the final solution here. And if someone wants to ask it out, then they can ask right now. I mean, related to the problem, not general doubts right now, but related to the problem. If someone wants to ask, then they ask. Okay, since no one is asking, I'll move on to the code now. Okay, so my code was this, that int t c in t, while t minus minus int xy c in xy, right? And the first case of x equal to y, then I'll do 2 into x minus 1. Like the number of equal indices will be 2 into x minus 1. And I'll subtract that from 2 into x plus y minus 1, which is the total number of indices, to get my final answer, right? And otherwise, whatever is the minimum, I'll do 2 into minimum, like 2 into y I showed you. So 2 into x plus y minus 1 minus 2 into minimum. And that is the answer. Okay. All right. So I'll move on to the next problem. Uh, this one is called big difference. Okay. You are given two integers n and k. Find any two integers a and b such that a and b are between 1 to n. Difference between a comma b is greater than or equal to k, and difference between GCD and LCM of them is greater than or equal to 2k. That is, your task is to find any two integers not exceeding n, so that they differ by at least k, and their GCD and LCM differ by at least 2k. It is possible that no valid a comma b exists, in which case you will print minus 1 twice instead. So the problem says that we have been given two integers n and k, and we want to print two numbers a comma b such that they are between 1 to n and their difference is at least k. A minus b absolute value is greater than or equal to k, and the GCD of a comma b minus LCM of a comma b का absolute value is greater than or equal to 2k, right? We want to print any a comma b pair, and also if there doesn't exist any pair, then we have to print minus 1 comma minus 1. Okay, right. So the samples. Okay, one sample is 6 comma 2. All right. So 6 comma 2 means n equals 6 and k equals to 2. So in this case, they have printed 4 comma 6. Okay. So 4 comma 6. Their GCD is 2, right? GCD is 2 and LCM is 12. So what is G minus L? It is 10. And 10 is greater than or equal to 2k, where k is 2, right? So that is 4, and 10 is greater than or equal to 4. And also they have printed 4,6, so 6 minus 4 is also greater than or equal to k, which is 2 here. So that's why the answer is correct, 4,6. And for 8,11, they are saying that there is no pair, so the answer is minus 1 minus 1. All right. So let's see how to solve this problem. So first of all, observe that this a minus b greater than or equal to k, and we want like them to be between 1 and n. So essentially what they're saying is the difference should be greater than or equal to k. It should be at least k, right? So okay, if both the numbers are between 1 to n, like 1 is here, 2 is here, and up to n is here. So if a and b both are between 1 to n, then what can be their maximum absolute difference? Like a minus b, maximum value, what can it be? In the worst case, like in the best case, we have a here and b here. That is b equal to n and a equal to 1. That is the farthest that they can be, right? So in that case, the difference is n minus 1. Okay. And So basically, we want that to be at least k, right? So if it is equal to, let's say k is greater than n minus 1, like in our input, if k is greater than n minus 1, then it is not possible to make that difference of at least k, because we can make the difference of at most n minus 1, right? So let's say we have n equal to 5. So maximum difference that we can make is 4 between a and b by taking a equal to 1 and b equal to 5. But they are asking if k is equal to 6, then they're asking me to make difference at least 6. So that is not possible, right? So that's why in this case, 8 comma 11, it is not possible. Like for n equal to 8, I can only make up to 7 difference, right? That's why the answer is minus 1 minus 1. Okay. So the first thing is that if k is greater than n, greater than or equal to n, then minus 1, right? The answer is minus 1 minus 1. Okay. So now we have been left with solving for k less than n, right? K less than n, sorry, not less than equal to, less than n. We have to solve, right? And we have to solve it such that their GCD minus LCM absolute value is greater than or equal to 2k. Okay, and first of all, like another thing, that this LCM is always greater than the GCD, right? That is pretty obvious. Like LCM of a comma b is always greater than or equal to GCD of a comma b. So that's why we can just write it as LCM of a comma b minus GCD of a comma b is greater than or equal to 2k. Okay, we want to ensure this thing, right? So I like first thing I thought is, okay, on a number line we have 1 to n, right? I have 1, I have n, and I want both of these numbers to be in this range from 1 to n, like a comma b to be in this range, and I want their difference to be at least k, right? So if k is large enough, I can just brute force, right? Basically, let's say k is this much, like let's say this is 2 and this is 8 and n is 10. So like, if let's say in this case k equal to 8 minus 2 plus 1, which is 7, so k is very large. So in this case, there are only limited number of options from where I can choose. Okay, so my point is, like, for example, if n equals to 10 and k equal to 7, then okay, let's assume that first of all a is less than b. Since a inverse symmetric, we can do that. Like, since a inverse symmetric, we can assume that a is less than b, right? So what can a be? A can be either 1 or 2 or 3. A cannot be 4. Why? Because um, b has to be at least a plus 7, right? Because we want their difference to be at least k. So if a is something a, then b has to be at least a plus 7. But b cannot be more than 10, right? So therefore a cannot be 4. So there are only limited number of options for what a comma b can be. So if a is 1, then b can be either 8, 9 or 10. If a is 2, then b can be either 9 or 10. And if b is 3, a is 3, then b can be 10. So in total there are 6 pairs, right? So the thing is that if k is large enough, then we can just brute force. And what is large enough? Like, what do I mean by large enough? What if we generalize this? Let's say we have something n minus k, value of n minus k is something, right? Like, okay, so a can be 1, a can be 2, and up to where can a can be? Like, up to where can a be? So let's say a is up to x. What does a is up to x mean? Ki x plus 1 a cannot be. And why it cannot be? Because in that case, b will not be able to have any value. So like in this example, if we keep a is equal to 4, then 4 plus 7, that is 4 plus k, was greater than n. So therefore we couldn't keep 4. So generalizing this, a, like a cannot be x plus 1, because x plus 1 plus k, if that is greater than n, then a cannot be x plus 1. So this means x is greater than n minus k minus 1, or we can say that x is greater than equal to n minus k. Then in that case, like we cannot have, basically we cannot have a to be that value, a to be x plus 1. So a can be at most n minus k, and in this case b can be only n. Okay, so for 1 we have 1 plus k, 2 plus k, up to n. For 2 we have 2 plus k for the value of b, up to n. And generalizing this, you can see that approximately it turns out to be n minus k whole square upon 2, or something like that. Like in this case, or maybe I can do it exactly. Like it will turn out to be 3 n minus k into n minus k minus 1. The number of possible pairs of a comma b, it will turn out to be this. Okay. So if k is large enough, that is if k is close to n, that is n minus k is pretty small, then we can just brute force, right? So we can say that we have like 10 to the power 4 test cases, right? And in 1 second we can do up to 10 to the power 8 operations. So if I take the limit of 50, like if n minus k is 50, I mean if it is less than equal to 50, then if I do the operation, like if I do a brute force, then it will take approximately 2500 steps, and 2500 into 10 to the power 4, that should run in 1 second. Like even in worst case, where for all test cases I have to brute force, then also this 2500 10 to the power 4, this is just 2.5 into 10 to the power 7, right? So this is less than 10 to the power 8. So this will run in 1 second. Okay. All right. So we'll do a brute force. And what is the brute force? We can just check for all pairs of a comma b whether this condition holds true or not. Like I'll run a loop of a from 1 to n minus k, and I'll run a loop from of b, nested loop, from a plus k to n. And here I'll check if a comma b pair is valid or not. And if it is valid, then I'll print it. And if it is not valid, then I'll continue. And in the end, if I've found no pair, then I'll just print minus 1, minus 1. Okay. Why n minus k less than equal to 50? Prince, I am saying that if n minus k is less than 50, then we can brute force. Because I am running a loop from 1 to n minus k, and n minus k to n. So basically my loop is of k into n minus k. Right? Or basically something like that. So if n minus k is small enough, then I can do brute force. So I'll just take arbitrary 50 value. Like I just took 50 value because approximately this is square loop, right? This is O of n square, O of n minus k square. So if I take just 50, like if I do brute force till 50, then in the worst case also it will pass, because for each test case I have to do 50 square operations. That is, I have to do 2500 operations, and there are 10 to the power 4 test cases, so it will pass. That's why I limited to 50. But what if n minus k is not less than 50? If n minus k is large enough, like okay, the one case that we handled, was that n minus k is less than or equal to 50. Okay. So what does this mean? That k is greater than or equal to n minus 50, right? But what if this is not the case? Like, what if k is less than n minus 50 as well? Okay, so this was the one case that we handled using brute force. But the second case that we handle, what can we do is, like, what I did, at least, what I did was just choose a as n. Okay, like I just chose a as n. We know that k is less than n minus 50, right? So, okay, we want that the gap between a and b is at least k, right? So if I choose a as n and I want this gap to be at least k, right? And I know that k is less than n minus 50, right? So, okay, if this is n and this gap is k, then um, this point is n minus k, right? So my point is that this interval 1 to 50, like this possible interval 1 to 50, will have at least 50 numbers. I mean, this interval 1 to n minus k, it will have at least 50 numbers, since k is less than n minus 50. Like, since this gap is less than minus 50, this gap will contain the numbers 1 to 50, right? So what I'm doing is, what I want to say is that I am keeping a as n. Okay, just a second. Yeah, I am keeping a as n, and I am saying that b can be up from 1 up to n minus k, right? Because I want their difference to be at least k. So what I'll do is, I'll fix a as n, and I'll search for a b between 1 to n minus k. Like, I'll start from 2. Okay, I'll start from 2 and I'll go forwards until I find a coprime number to a or n. Like, I have set a equal to n, right? So I'll start from the start from 1 and I'll move up. I'll start from 2 and I'll move and I'll stop at the number such that GCD of a comma b is equal to 1, means they are coprime, and I'll definitely find such a number within 50, because coprime gap is pretty small. See, what I want to say is that I'll definitely find such a number between 1 to 50 such that their GCD is 1. Like, GCD of n comma b is 1, because it is not possible that n is a number up to 10 ki power 9 and it has a factor of 2 also, 3 also, 5 also, 7 also, and up to 29, whatever, 29, 31, 37, all of these primes, if you multiply them, then it will go greater than 10 to the power 9. So my point is that if n is a number which is less than 10 to the power 9, then it cannot happen that it has all of these numbers as a prime factor. So at least one of these numbers will be coprime to n. Okay. So I will find a number coprime to n soon enough, and I'll just choose that as a b. So basically my a is an n and my b is a number. Suppose it is m, such that GCD of n and m is equal to 1, right? So if we try to verify our condition, that is L minus G greater than or equal to 2k, so in this case G is 1, right? Since we have found an m such that G is 1, so G is 1 in this case. And what is L? Since they are coprime, since A and B are coprime, so the LCM is just A into B, or we can say N into B. So what is L minus G? It is N into B minus 1. And since I started b from 2, right? Since b is greater than or equal to 2, this n into b minus 1 is at least greater than or equal to 2 into n minus 1. So it is at least equal to 2k minus 2. I mean 2k. Like, since k is less than n, right? We were solving for the case where k is less than n, or in fact, it is less than n minus 50 also. So if my LCM minus GCD, so this NB minus 1 is my L minus G, and it is definitely greater than 2n minus 1. So it is definitely greater than 2k because k is pretty small compared to n, right? So that's how I solved it. But yeah, some of you are saying that there exists an easy solution. So I'll read the chat once. Take the smallest prime number, that is 2, and okay, someone wrote a solution that we can take either 2 comma n, or we can take 2 comma n minus 1. And if they both don't satisfy the condition, then we can print minus 1 minus 1. So actually, this might be correct, I don't know, because I have not proved it yet, and my job is to tell you as a solution which I know the proof of, like which I know it is correct. So, and also in the contest also, I try to do solutions which I know they are correct. So I just submitted this one, that for small n minus k, I just do brute force, and for k less than n minus 50, like if I have enough numbers to choose from 2 to 50, like if k is small enough, then I'll choose one as n, and the other I will find from 2 to 50, so that is coprime to n. And since it is coprime, so L is pretty large and the GCD is pretty small. So that was my idea here. Okay, guys. I hope it is clear to all. So I'll move on to the code. Like, my solution might not be elegant, but it is correct at least. Like, it is provable to be correct. Okay. And yeah, as you can see in contest, my submissions, many submissions, because these were initially wrong for some reason. So I had to try again and again. But after that, they all got accepted for some reason. Okay. So yeah, my solution was, okay, seen int nk, seen nk. If k is greater than or equal to n, then print minus 1 minus 1. This was because we can only have n minus 1 gap at most. Okay. Now, if the gap is small, we can just brute force. Like, I am doing a is equal to 1, a less than or equal to n minus k, and a plus plus. And b starts from a plus k, b less than or equal to n, and b plus plus. And if it satisfies the condition that LCM AB minus GCD AB greater than or equal to 2 into k, then I'll print a comma b, and I'll return, right? And after all of this, if I did not find a number, if I did not return, then I'll print minus 1 minus 1, because I searched all the pairs and I did not find one, right? And otherwise, that if k is small, that is, I can find a number b, like a is n, and b I'll start from 2 and do b plus plus. So as soon as I find a number which is coprime to n, like that is GCD of a comma b is 1, then I'll just print those two numbers, because LCM of a comma b will be a into b, and that will satisfy the condition. So I'll print that and I'll return. Okay. So do you all get the solution? All right. If I don't, I am not getting any doubts, so I'll move on to the next problem. Okay, so this is minimum colors easy, minimum colors hard, and smoothly increasing. These three are the problems that are remaining. So I'll do this one first because these easy and hard version are connected to each other. They are pretty similar to each other. So I'll move them and I'll do them at the end together. Okay. So I'll do this first. Smoothly increasing. For an array B of length m, it is said to be smoothly increasing if it satisfies either the following conditions. Either it is of length 1 or it is strictly increasing and the difference array is smoothly increasing. That is, an array is smoothly increasing either as length 1 or it is strictly increasing and is whatever I said. Yeah, that's what I said. The definition is recursive. Yeah, basically, to check if an array is smoothly increasing, you have to find its difference array and check that its difference array is smoothly increasing, right? And you will do that until the length is up to 1. For example, these arrays are smoothly increasing while this one and this one are not. So let's think about that what they are saying, that 1 is smoothly increasing because it has length 1. Okay. 5 comma 9 is smoothly increasing because it's different. Okay, because it is, first of all, it is strictly increasing, right? It is strictly increasing and its difference array. The difference array, what is it? It is 4. 9 minus 5. So 4 is also smoothly increasing because it has only one element. So that's why this entire array is smoothly increasing. And also this 10, 100,000, this is also smoothly increasing. Why? Because, okay, we have 10, 100 and 1000. So if we take the difference, like 990, and then we have, sorry, not 990, we have 90, the first one. The first difference is 90 and second difference is 900, and the difference array of this array is 810, right? So this is also increasing, this is also increasing, and this is of length 1. So that's why this entire array is smoothly increasing, right? The definition is that. Okay. Given an array of given an array A of length n, for each index, answer the following question independently. Delete the element AI from A without changing the order of the remaining elements. Is the resulting array smoothly increasing or not? That's what we have to find out. Like, we have been given an array, for example, 1, 2, 3, and 4. We have been given this, and for every element, like basically we have to delete that element. So the remaining one is 2, 3, 4. Let, if we delete this one, then remaining is 2, 3, 4, and we have to comment whether it is smoothly increasing or not. And if it is smoothly increasing, then we have to print 1, and if it is not, then we have to print 0, right? And we have to do this for all the indices. Like, we have to delete all of these ones one by one and check that whether they are not, and print whether they are not smoothly increasing or not, whether they are, right? You get the point. So the sample test cases, if I see, like, I think it is not very productive to look at samples. Like, I think you all would get the samples, right? Like, is there anyone here who doesn't get the samples? Like, is your answer different from the output? Someone, is there anyone like that did not get the answer? Okay, yeah. So I am assuming that every one of you know that how the samples answer came. All right. So I'll just move on to explaining solution. All right. So, okay, just think about what is the definition of smoothly increasing, right? That basically we have an array. Let's say we have A1, A2, A3, and A4. Now, first of all, for it to be smoothly increasing, it has to be increasing, and also its difference array, that is, if we make a2 minus a1, a3 minus a2, and a4 minus a3, this array has to be smoothly increasing. So what does that mean? That its difference array, like if I call this b1, b2, b3, then its difference array, that is b2 minus b1, comma b3 minus b2, this array also has to be smoothly increasing. And what does that mean? That this has to be increasing, and its difference array, that is, maybe if I call it c1 and c2, then c2 minus c1, this one element array has to be smoothly increasing, and it is by definition smoothly increasing, right? So basically, if we just follow this definition, what we can say is that all of the difference arrays have to be strictly increasing. All right, that's my point. That this array has to be increasing, this array has to be increasing, and this array has to be increasing. Right? That's my point. That for the original array to be strictly increasing, we have to have these conditions. Okay. So do you guys get up till this part? That for an array to be smoothly increasing, it has to be like all of the difference arrays one by one have to be strictly increasing. Like that condition is necessary and sufficient. All right. So I hope until here it is good. Okay. So now let's think about what is the minimum possible array that you can get. Okay. Like basically, just think about what is the smallest possible array that you can make, which is strictly increasing. By smallest possible, I mean it contains the least values, smallest value as possible. Okay. So let's say we have an array. Okay. Now to think about that, just think about it in reverse. Like what we want is, we want our all the difference arrays to be increasing. So to think about what is the minimum possible array, think in reverse. Okay. What do I mean by that? That okay, let's assume that the last difference array is what? Let's say it is 1. Like basically the last difference will be a single element, right? Like for example, if I had the array of 1, 10, 100 and 1000. So the first difference array was 9, 90 and 900. Second difference array was 81 and 810, and the third difference array was 810 minus 81, whatever that is. Okay, whatever that is, like, okay, so this is one element. So what I'm saying is that the last difference array will have just one element, right? So in the best case, like what will you choose it to be? If you want that our original array is minimized, then what will you put the last difference to be? You will try it to be 1, right? Like basically, let's say you want to make an array of 2 length. Okay, so let's say if you had put 2 here, not 1, then the minimum possible array that you will get would be 1 comma 3, right? Because the minimum element is 1. Like in the array constraints, the minimum element, like the range is up to 1 to 199. So minimum is 1. So you have to put 1 here, and to ensure difference of them is 2, you have to put 3 here, right? So instead of doing that, what if we just put 1 here? Like as a difference, if we put 1, then if I start this array with 1, then I can take 2 as well, 1 comma 2, right? That's why I'll put 1 here. Note that I cannot put 0 here. I cannot actually put 0 here. Why? Because in that case, this array would not be strictly increasing. This is not strictly increasing, and that's why it is not a smoothly increasing array. So it will not generate a valid smoothly increasing array. Okay. So that's why I have to put 1 in the above case. So let's say I put 1, and basically this is a difference array, right? This is the last difference array. So what about the second last difference array? Like here we'll have two elements whose difference is 1. So let's say that they are 1 and 2. In the minimum possible case, they can be 1 and 2, right? So 1 and 2 have a difference of 1. Now what about the third difference array? I mean the third last difference array. Basically the difference array of that array is 1 comma 2, right? So if we assume that the first element is 1 of that array, then second element is 1 plus 1, which is 2, because we want the difference of 1, 2 and 1 to be 1, right? And the third element will be 4, because we want 4 minus 2 to be 2, right? So 1 to 4 we get. And so this is the minimum possible smooth increasing array of length 3. What about length 4? Like if we want length 4, then we have to put 1 here, 2 here, then 4 here, then 8 here, right? So for a length 4, this is the smallest possible smoothly increasing array. So this is the power of 2. Like if you see the pattern, then it is the pattern is that the smallest smoothly increasing array of size n is basically the sequence of 2 key powers. So it is 2 to the power of 0, 2 to the power of 1, up to 2 to the power of n minus 1. Okay. So if you want to make a smoothly increasing array of size n, then the smallest possible you can go is 2 to the power 0, 2 to the power 1, up to 2 to the power n minus 1. Right? So if I tell you to make a smoothly increasing array of size 35, let's say. Okay. See, my point is that these elements grow exponentially. These elements grow very fast. But since the limit on AI was up to 10 to the power 9 only, we can say that arrays above certain length cannot be smoothly increasing. Why? Because let's say you want to create a 35 length array which is smoothly increasing. Then what will you create? You will create 1, 2, 4, 8 up to 2 to the power 34. So this is the minimum possible array of length 35, which is smoothly increasing. But 2 to the power 34 is not possible. Like in the input, it will never be in the input this big of a number. So we can say that if we have been given an array which has all the elements less than or equal to 1e9, and it has length greater than or equal to 35, then we can say that it cannot be smoothly increasing. Or even 32, we can say, like even for 32 we can say that it cannot be smoothly increasing, right? So we want to comment for all the arrays by deleting each element, right? So we have been given an initial array A of length n, and we have to delete each element one by one and comment on the resulting array. So since the initial array is of length n, so the final array is of length n minus 1, and we have to comment if that n minus 1 length array is smoothly increasing or not. And since we know that if n minus 1 is greater than or equal to 32, then it cannot be smoothly increasing. So if n is greater than or equal to 33, then the answer is no. We don't need to do anything. The answer is definitely no. Because the limit of elements is up to 10 to the power 9 only. So just to be safe, I just did that if n is greater than or equal to 35, then you can say that for all the elements, if I delete one by one, like if I delete the first element, then also the answer is no. If I delete second element, then also the answer is no. So for all the elements, the answer is no only. So The answer is 0, 0, 0, 0 n times. And if n is less than or equal to 35, then what will you do? Tell me, guys, what will you do? Or n is less than 35 or something. Then what will you do is, anyone? You can basically do brute force. For n less than 35, you can do brute force. Why? Basically, what you can do is, even in O of n to the power 4 would pass. But I'll do it in O of n cube for you guys. Okay, so O of n cube also passes because n is just 35. So how will you do it in O of n cube? See, you have an array a1, a2, a3 up to an, and you have to delete elements one by one. So let's say you first delete a1, then check this array, then delete a2, then check this array. I mean, uh, this array, right? Then you delete a3 and so on. So this will take n into whatever checking time is, time for checking. Like this will take n into the amount of time we take for checking whether an array is smoothly increasing or not, right? And in how much time can we check that? Basically, what I told you was every difference array has to be increasing, right? So first of all, this array has to be increasing, then its difference has to be increasing, then its difference has to be increasing, and so on until you get length 1. So there are n difference arrays, right? Because initially you have length n, then length n minus 1, then length n minus 2. So basically there are n difference arrays, and we have to check for each one of them whether they are increasing or not. So we can do it in O of n time for each of the arrays. Like we can check this in O of n time. We can check this in O of n time. So we can basically check the entire thing in O of n square. We can do it in O of n square, that whether an array is smoothly increasing or not. So in total we can find the answer in O of n cube. So if n is less than 35, just apply this O of n cube solution, and otherwise print no, like just print all zeros. Okay, I hope it is clear. If anyone has a doubt, then they can ask right now. Not able to think this in context. Actually, same here. I mean, due to the um, thing that happened in div 2b, like after that my brain stopped working or something. So, but yeah, this was a nice question. All right, so if it is clear to all, I'll show you the code. The code is pretty simple. Okay, int and cnn, input the vector. That is, this iv is my macro to input the vector. Okay, that it defines a vector and it inputs it. All right. Now, if n is at least 35, then I'll print 0. For int I equal to 0, I less than I plus plus, I'll print 0. I'll print new line. I'll return. Right. Otherwise, I'll just do a brute force. So as you can see that this is one for loop, another while loop, and another for loop. So this is O of n cube approach. Okay. So this for loop is for which element to delete, which element we want to delete. Okay. So for int I equal to 0, I less than I plus plus. vector of LLV equals to A. So I made a copy of A, and then I erased the ith element from the vector. Okay. Then I have a flag. The flag which states that whether my V is smoothly increasing or not. So while V dot size is greater than 1, what I'm doing is I'm checking that whether V of I is greater than V of I plus 1. I mean greater than equal to. If that is the case, then it is not strictly increasing. The current thing is not strictly increasing, so I'll do flag equals to false and break. Right? And otherwise, I'll just take the difference area of V. Like I'll take the V, I'll take difference area of V, and I will like see basically what I'm doing is in the vector U, I am making the difference area of V, and then I am swapping U and V. So what that does is now inside of V there is difference area of V. So the length of V has decreased by 1. Okay, and eventually it will reach 1. So at that point this while loop will terminate. Right? But if like earlier we had flag equals to false, then we'll break. Like basically if we had some non increasing some non increasingness, then we just do flag equals to false and break, right? And then finally we just see out flag. And how does this flag is boolean, right? Flag is a bool variable. So if I do see out, then if flag is true, then it will print 1, and if flag is 0, then it will flag is false, then it will print 0. So it works perfectly. And then I do this for all of the indices. For int I equal to 0, I plus plus, I just print whatever the value is of the flag, and in the end I'll just print a new line. Can we do minimum color with 2 pointers? I am moving to that, but I don't think it can done with 2 pointers. Like everywhere I have seen only a DP solution, and I'll also create a DP solution. I don't think it can be done with 2 pointers. Okay, so this was the code for smoothly increasing array. All right, let us move on to these two problems: minimum colors easy and minimum colors hard. All right, so easy version first. We'll do. You have an array A of an integers. You can perform the following operation as many times as you want. Choose LR such that 1 is less than equal to n, less than r, less than equal to n. So we have to select two indices and AL equal to AR. So if, okay, then update AI to AL for all I from L to R. Okay, let f of A denote the minimum number of distinct elements in the array A after applying the operations optimally. You need to answer FA. We have been given FA, we have been given the array A, and we have to answer the f of A value. Okay. So like basically what I'll explain the problem again. We have an array. Let's take some example. Okay. Let's take this example 1 2 1 2 3 2. Okay. So we have 1 2 1 2 3 2. So in one move, what we can do is we can basically select any two indices L and R, okay, such that their value is same. Like for example, if I choose this 2 and 2, their value is same, and to the entire sub array from L to R, I can just replace this value with the endpoints value. So I'll replace all of these values with 2. Okay, so that is the operation that we can do. So we have to determine the minimum number of distinct elements that we can make in this array if we perform the operation optimally, and we can do the operation as many as we want. Like we can do it as many times as we want, right? So there is no limit on the number of times that we can do the operation. Okay. So in this test case, what we can just do is, obviously we cannot make the entire array equal. Like for that, we would have to have the same element in the first and the end, right? So we cannot make the entire array equal. So what we have to do is, what we can do is, we can just select these two elements, and the array will become 1, 2, 2, 2, 2, and 2, right? So in this case, we have two distinct elements. So the answer to this test case is 2. This is the answer to this is 2, right? And if we have 1, 2, 1, 2, then also in this case we cannot make it 1, but we can make it 2 by selecting this subarray 1, 1 and 1, and just converting this 2 into 1. Or actually, we don't need to do that. Like initially, also there are only two distinct elements, so the answer is 2. And then in this 1 to 1, what we can do is select this one and this one, and the entire array becomes 1. So there's only one distinct element. And in the last one, we cannot do anything because there are no duplicate elements. We cannot select any subarray. So that's why the answer is 3. We cannot do anything, any operation. Okay. So let us think about how to do this problem. Okay. Now, first of all, just imagine this operation as something else. Like I'll make you visualize this. Okay. We have this array, right? Let's say that we applied an operation here. Okay. And then we applied an operation here. So what does that mean? That means that, okay, since we applied these here, these two were equal, A and A. They were equal, right? And then, okay, we applied it. So here also A and A will come, right? And now since we are applying on this subarray, that means that this index and this index are also equal. So here also A and A, right? So what I can say that in this original array, in the original array, sorry, yeah, what I'm saying is, in the original array, this element, and this element were equal to A. Like maybe these two elements became equal to A after we did the first operation, but these three elements were equal to A initially in the array. So what my point is that instead of doing this, instead of doing this one and this one, we could have just done this entire thing. Just select these two A's, and doing this thing will also change the entire subarray to A. Okay. So my point is that you will never do something like this. Okay. Why you will never do this? Because instead of doing this, you can just do this, right? And similarly, you will never do something like this. Something like what? Something like, let's say you first do this and then you do this. Like let's say there was A and A here, and you chose this subarray, and then you chose this subarray. So there was B and B here, let's say. So initially, after performing this thing, this subarray becomes A and A, right? But after doing this entire thing, it becomes complete B. So instead of doing that, you could have just done only the below operation. Like you could have just not done this and just did this one, and that also would have affected in the same way that the entire subarray becomes B. Like there is no point in doing first this operation and this operation and then this operation. You can just directly do this longer operation. Okay, that's my point. That in optimal way, you will never do this, and also you will never do this, right? So definitely your intervals won't intersect. Like whatever operations you are doing, they will never intersect. All right. So you will always. So okay, what is left then? If you will not do this one, and you will not do this one, then um, you will do only this thing, like only like this, right? This is the only possibility left. That you will select disjoint subarrays from the array and do the operation in them, right? That is one thing to notice. That is one claim of mine, and I hope you all get it. Okay. If you don't get it, then you can rewind the video. I think I've explained it well, right? Okay, so that was my claim one. What is my claim two? My claim two is that you will never do the operation on the same number. Like let's say you have done this operation on 2 and 2. Like there was a 2 here, there was a 2 here, and you selected this subarray and made the entire array 2 2 2 2. So you will never do this. I mean, okay, see, sorry. What I'm saying is you might do this, but what I'm saying is you will never repeat that operation. Like you will never do it again. That 2 2 2 2. You will never do it again. Why? Because instead of doing this, you can just do this entire subarray. Because that will just make the entire thing as 2 2 2 2 2 2 2. Even the remaining, the middle elements, they will also become 2. Right? So that's why you will never repeat a number. In the optimal case, you will never repeat a number. Okay. Because doing this thing can only make your answer better or make it the same. Right? That's my point. So now, like basically, you might have seen this pattern in DP. Like in some DP questions, you might have seen this pattern that we have to do the operation on subarrays. Like on disjoint subarrays, we have to do something on operation, and we have to find the optimal answer, right? So in that case, we can easily do a DP. So my DP state is just simply that DPI is my answer for array of 1 to I. Like if I consider 1 based indexing, or okay, let's consider 0 indexing. So it is the answer from, if I consider just the array from 0 to I. Like I have the entire array, right? A0, A1 up to AN minus 1. Okay. Then this dp of I is just considering all the elements up to I. That is AI. Considering this array, what is the answer for this array? That, like, what is the minimum number of distinct elements that we can achieve in this array? Okay, right? So that is my state. Okay, now how do I transition from this? So let's say I have already calculated the answer for 0 up to I minus 1, right? And now I want to calculate the answer for dpi. So what does that mean? That means that I already have the answer for a0, a1, a2, and so on up to a of I minus 1, and I want to insert ai, right? So now there are two possibilities. Okay, one possibility is that while doing, like while inserting this ai, either, okay, see, you have to do operation on subarrays, right? You have to do operations on distinct subarrays, I mean on disjoint subarrays. So it will look something like, maybe you have done operation here, maybe here also you have done. So either it will be like you have done an operation on this ai, like ending at this ai and starting somewhere, or it will be that you have not done an operation on this AI. Okay. So let's say that you have done an operation on this AI. Okay. So in that case, like basically, let's say that AI is 5 for now. Okay. Let's say 5 is written here. So for you to do an operation on here, there has to be another 5, right? Basically, if you are choosing this as endpoint, if you are choosing this as R, then an L also has to be a 5, right? So just choose this L to R, and all of these will be 5. Like from this L to R, this entire array will consist of 5. Okay. So essentially, if you have chosen A of L, like if you are doing an operation on AI, that means that you have an L. You have an index L such that A of L equals to A of I. And you are doing the operation on the subarray L to I. Alright. So that means that I can just calculate my answer for DPI as the answer for up to L minus 1. DP of L minus 1 plus 1. Why? Because um, that is pretty obvious. Like A0, A1 up to AL minus 1, AL, and up to basically A of I. So what you are doing is you are doing an operation from AL to AI, right? Where the value of AL has to be equal to value of AI, and you have to find the minimum value. So basically, what I can say is you have done operation on this subarray, and since your operation is disjoint, you will do the operations only on this array. So basically, your answer is just the answer to this array plus the number of elements in this. That is just one. Like this entire subarray consists of only one element, right? So that's why the answer is the entire DP of I. So DP of I is DP of L minus 1 plus 1. If you do the operation on I, like if you do the operation from L to I, where L is some index such that A of L is equal to A of I, then your DP of I will be DP of L minus 1 plus 1. Or it might happen that you don't do an operation on I. Like in that case, your answer is just the answer for this I minus 1 array and plus this one extra element. So your answer is dp of I is dp of I minus 1 plus 1. So you have to take the maximum of these two. And in fact, not doing the maximum of these two, you have to take the maximum of all of those L's, like all those indexes, such that they are equal to AI. Like let's say we have an array where we are calculating the answer for I, right? This is index I, and A of I is 5, and we are calculating the answer for I. And let's say that 5 occurred here, 5 occurred here also, 5 occurred here also. So either you can do this operation, or you can do this operation, or you can do this operation. So there are multiple options. So whichever one is giving the maximum value of dp of L minus 1, also I mean the minimum value, then that one you will take. Or if you are getting the minimum using this one, then you can take that also. So basically dp of I is the minimum out of all of these possibilities. uh, this is buggy kind of for some reason. Yeah, so out of all of the L's, whichever one is possible as your answer, you can basically um, take that and add 1 to it, like dp of minus 1 plus 1, right? But now someone might ask that why am I adding plus 1 here? Like someone might have a concern that what if in the dp of L minus 1 thing, there is already an element. Like, okay, what we are saying is that, let's say we do an operation on this 5 and this 5. So what we are doing is taking the answer up to here, the dp of L minus 1 up to here, and adding 1 to it. 1 because of counting this 5. But what if there was a 5 in this array only? Like, if there was a 5 in this array and we did not, uh, like, it is still there after the operations, after the optimal operations, it is still there, then we don't have to add a 1. Like, someone might ask me that, like, what if there is already a 5 in the optimal subarray here? Then why are we again adding dp of L minus 1 plus 1? So why am I doing plus 1 here? Like, it is possible that 5 is already in the array. So this sequence of 5s should not be counted as a separate distinct element. But my claim is that you don't need to worry about that. Like, um, why do you not need to worry about it? Because there's always one method. Like, see, I proved that this thing is right. Like, you will never do something like this two. Like, you will never do something like this, these twos and these twos. You won't do anything like this. You will definitely choose this entire subarray of 2, right? So if there were any 5s remaining in the dp of L minus 1, then it will be handled. Like, definitely we will get a more optimal answer than this by just choosing all of these 5s. And in the end, what we did here plus 1 won't matter. So automatically it is being taken care of. Like, because if there wasn't a 5 there, like, if in the up to L minus 1 there is not a 5 and we just do on this one, then of course dp of L minus 1 plus 1 is correct. But if there was a 5 in the optimal ordering, then automatically our dp will handle it, because it will choose this 5 instead of this one. Like, it is more optimal to not choose this 5. So automatically we'll get a more better answer if we are just doing this transition, right? So my final dp is actually not final, but my correct dp is that um, dp of I is the minimum over all L, such that AL equals to AI of dp of L minus 1 plus 1, and also the minimum with dp of I minus 1. All right. So basically, you either do an operation on I. So for that, you need an L such that AL equal to AI. So in that case, the answer would be dp of L minus 1 plus 1. Or you don't do an operation on I. So in that case, okay, the answer is 1 plus dp of I minus 1. Okay. So just take the minimum of these two. But the thing is that n is up to 2e5, right? And this approach seems n square. Like, it seems like it will take n square time to calculate this. Like, ideally what you would do is just iterate over all the indexes and check, like, see if you are updating the dp for I. Okay, you are updating dpi and you want to update it, then you will iterate from 1 to I minus 1 and just check for every j or every L that whether AL is equal to A of I or not. So if it is equal to A of I, then you will update. that dp of I equals to min dp of I comma um, dp of n minus 1 plus 1, right? So this is n square approach. But how will you optimize this to O of n? Like, to optimize this to O of n, what we can just do is store the minimum dp for all different numbers. So see here, the numbers are up to n only. This ai is from 1 to n only. So what you can just do is store the optimal answer for all the numbers. Like, see, let's say I have this example that I have a 5 here, I have a 5 here, I have a 5 here, and ith element also I have 5. So now to transition, I have three possibilities: to either take this 5, or take this 5, or take this 5. So to choose, like, to transition now, I can basically store the value of dpl minus 1, the minimum value of dpl minus 1, basically. Like for this 5, so okay, let's say that the dp, or I'll draw it neatly down there. So let's say that this is the array. This is the array A. We have a 5 here, a 5 here, a 5 here, and a 5, let's say, at the ith element. And let's say the value of dp is, let's say, 1 here, 2 here, 3 here, 2 here. And right. And like this is not relevant, this 2 is not relevant. So what we'll just do is we'll keep an array. We'll keep an array called mi, which is of length n plus 1. Like it will store the minimum dp value for all the numbers from 1 to n. Like for 5, what will it store? It will store 1. Because basically for this 5, the dp of l minus 1 is 1. For this 5, the dp of l minus 1 is 2. For this 5, the dp of l minus 1 is 3. So what is the minimum value of dp l minus 1 for all the 5s? It is basically 1. So mi of 5 will just store 1. And as we are iterating over the array, we will update this minimum. Okay. Like, since we are here, like let's say we calculate this dpi. We are done with this dpi. So what will dpi be? Dpi will just be, in this case, the mean of mi of 5 plus 1, or dp of I minus 1 plus 1. So you have dp of I updated, and also you have to update mi of 5 now. Like mi of 5 will be min of mi of 5 comma dp of I minus 1. So for this I, whatever the value of dp of I minus 1 is, you have to take the minimum. So you are tracking all of the previous 5s that have occurred and keeping the minimum value for them, so that we can efficiently update the dp for each future element. So dp of I is min of mi 5 plus 1 and dp of I minus 1 plus 1, right? Yeah, use extra array, exactly. So you are storing the minimum possible dp value for all the numbers, and initially it is just infinity, right? Initially for all the numbers it is infinity, and as you are iterating, you can update it if you encounter an element. All right. So yeah, that is the final solution to this. Okay. I hope it is clear to all. If anyone has a doubt, then they can ask right now. I appended the array to itself and tried to find the number of additional elements from R to n plus L. Can't we do it? I actually don't get your approach. Like, what are you saying? Using segment tree. Uh, like, I don't really understand what your solution is. So I don't think, I think it is pretty complicated to explain on chat, right? Anyways, I'll show the code now. Okay. So I have this simple code right here. I have this array A, which I took the input, and I have the array of DP. And also I have the array of MA. Actually, this MA is mislabeled. It should be MI. The name is pretty misleading. It should be MI, okay? I have MI of n plus 1. And initially I set it as infinity. Okay. Then DP of 0 is 1. Like the base case is this, that the DP of 0 is 1. Why it is 1? Because we can basically, like, DP of I is the answer for prefix I, right? So if we just consider the first element, A0, if this is the array, then the answer is 1, right? That is why the DP of 0 is 1. And MI of A of 0 is 0. So why have I done this? Like, basically I have recomputed the, for, like, I equal to 0 case. Like, this is the base case, right? So I have basically updated the MI of A of 0. So why have I done that? Like, let's say the array is 5 4 5. Okay. So when you're iterating, you will start, so this is the base case. So the DP is 1 in this case. Then you will go to this and update the DP. Then you will go to this, and you will try to access MI of 5, right? And ideally our MI of 5 should be 0. Why? Because we can take this array and our answer will be 1. So since I am doing 1 plus MI of 5, my MI of 5 should be 0 to give the correct answer. Or essentially what I am doing is I am defining this DP to be 0. Like the empty array, the DP for that to be 0. And basically I am just taking the minimum of MI of 5. So yeah, that is one way to think about it, that for the DP of empty array, I am considering it to be 0, and I am storing that value in the A0. Just like I am storing 1 in the MI of 4, I am storing 0 in the MI of 5. Okay. Then for I equal to 1, I less than and I plus plus. DPI is min of DP I minus 1 plus 1, or MA of A of I plus 1. So like basically MI of 5 plus 1, and MA of A of I equals min of MA of A of I comma DP of I minus 1. So we are just updating the MI array like I did here, that as we are iterating, we just update the MI of 5 with the previous value, MI of 5 with the previous value, MI of 5 with 1, right? So at the ith index, we'll update that. And the final answer is just the DP for entire array. That is the DP of n minus 1. Okay. So yeah, that was it for this problem. And this problem is remaining, that minimum colors hard. Okay. In the hard version, it is that there are some, like it is the same as easy version, but there are some elements for which the value of AI is equal to 0. Okay. And basically, it is up to us. It is up to us to replace that value with anything that we want. Like we can replace 0 with any element, and we have to optimally replace those zeros so as to minimize the final answer, that is f of a. Okay. So yeah, that is the hard version. And see, if you know the answer to the easier version, I think it is pretty straightforward to build it up to the hard version also. All right. So actually, in this one also, we'll use DP. Okay. So in this case also, the DP of I, what I'll define it, DP of I is the answer of the array from 0 to I. इसका आंसर. Okay. And also again I will keep another array, that mi of I is the minimum value of dp of l minus 1 for all the indices such that a of l is equal to I. So like mi of 5 stores all the dp of l minus 1, like it shows the minimum value of the dp of l minus 1 such that a of l is equal to I. A of l is equal to 5, whatever. All right. So yeah, this is the, like the two arrays that we maintain. Okay. Like in the previous version also, we maintained these two arrays, and also in this one we will maintain these two arrays only. Okay. So what we actually do is, see, let's say we have already calculated the answer up to I or I minus 1. Okay. So we have A0, A1, A2, A3, and so on up to A of I minus 1. And we want to calculate the answer for A of I. Right. Now there are two cases. Okay. One case is that A of I is 0. First case is A of I is 0. Okay. So in that case, what can we do? We can basically set 0 to anything, right? We can change 0 to anything. So we'll just change 0 to the first element. Like whatever there is on the first element, let's say there is 5. Then I'll change this 0 to a 5. And then I'll do an operation on this 5 and this 5. So the entire array becomes 5. So the answer is 1 in that case. So if a of I is equal to 0, then dp of I becomes 1. Okay, that is one case. But if it is not equal to 0, if a of I is not equal to 0, then what we'll do? Then basically we have to find a number. Like let's say a of I is not 0. So let's say a of I is 5. Right? So in previous one, what we did? In previous one, what we did was we found all of the 5s. Right? And we chose the one with the minimum value of dp of l minus 1. Like we found all of the l's such that a of l is equal to 5, and we did 1 plus dp of l minus 1. right? Okay. So basically, because we had to do the operation with a five, with a five only, right? But in this case, what we can do, we can either find a five. Like let's say we want to do an operation on AI. Okay. If we didn't want to do an operation, then it is just one plus dp of I minus one. Okay. Like if we don't want to do an operation, then it is just one plus dp of I minus one. But if we want to do an operation, then we have to find a 5, right? In the easy version, we had to find a 5, and the answer is 1 plus dp of L minus 1. But in this version, what we can do is we can find any 0 as well. Like let's say there is an array, like in our array, there are some zeros, right? So let's say there's a 5, there's a 0, there is a 5 here, a 5 here, and a 5 here. So we are at I. So either we can do it on this operation, we can do the operation on this subarray, or this subarray, or this subarray, or we can even do it now on this subarray. Like how? Because we can just choose 0 to be 5, right? Basically, the meaning of 0 is that we can replace it with any element, right? So we can just make 0 to be a 5 and do the operation on this subarray only. So in that case, if this index is L, then that is also the answer is 1 plus dp of L minus 1. Okay. So basically the only change here is that if we have a 5 here, if we have a 5 here, then we can either search for a 5 for the L index, or we can search for a 0 also, right? So basically just maintain and like in the mi array, in the mi array just maintain mi of 0 as well, like just maintain mi of 0. What is mi of 0? Mi of 0 means the minimum possible dp value for an index whose value is 0. Like for all al equal to 0, the minimum value of dp of L minus 1. Okay. So if you just maintain that also, then while transitioning, either you can do like either you can not do an operation on AI, or you can do an operation on AI and also find another AI in the array. So that means that 1 plus mi of AI, or you can find a 0 and do an operation using that. So that will have 1 plus mi of 0, right? So whatever is the minimum of these three, that is just your answer. Okay. And also you will update this mi of AI to be like when you are on the current index, you will keep updating mi of a of I to be like minimum of the current value, comma dp of I minus 1. Like similar to what you did in the previous case. So in the previous case, the difference is that here, if AI is 0, then dpi is just 1, right? And if AI is not 0, then we have to find either an AI or a 0 to do an operation. Or maybe we don't do an operation, then that is just 1 plus dp of I minus 1. Alright. So that's the only difference between these two versions of the problem. And that's the solution to this problem. So I hope it is clear to all. Is it clear to all? Everyone? Okay, since I'm not getting any doubts, I'll just move ahead and show you the code. The code is pretty similar to the first version. Okay. So again, what we are doing is just take the input for AI, right? Int and scene and ARR and scene ARR 5, and we have two arrays. First is DP of n, and another one is MI of n plus 1. And for all MI, I set it to like a very big number, infinity. Okay. Then MI of ARR 0 is 0, and DP of 0 is 1. Like similar to what we did in the previous case. Now for int I equal to 1, I less than I plus plus. If array of I is 0, then DP of I is 1. That is what I told you. And MI of 0 is basically either DP of n minus 1, I minus 1, or what is the current value only. Right? So we just update MI of 0 when we are at 0. Correct? And if ARR of I is not equal to 0, then either we do node operation, so it is just 1 plus DP of I minus 1, or we do an operation using ARR I in the array, or we do an operation using 0 in the array, right? So whatever is the minimum of that we'll take, and plus 1, right? So that is the DP value, and we'll update the MI of ARR I to be DP of I minus 1 or MI of ARR I, whatever is smaller, right? So that's the DP here. And finally, the answer to this problem is like the DP of entire array or DP of n minus 1. All right. I hope it is clear. Okay. So if it is clear to all, then I would end the live stream. So not clear. So which part did you not understand? Or maybe you can, since this is a YouTube stream, you can basically rewind the video and try to look at it again, right? So like if a small part is not clear to you, then I'll explain. Otherwise, you can just rewind the video again. Okay, so for the rest, I'm assuming that it is clear. All right, so I will just end the stream now, and thank you all for watching, and have a good night. Bye bye.